In this next video, we're going to take a look at another kind of log transformation function where you take the log of the response plus some number alpha. That is, well, you take the response, shift it by some number, and then take the log of that. Okay, and there's actually a package in R that'll do that for us. Let's open up the leaf burn data from Faraway, and I'm going to build a linear model, okay, for this variable called burn time. And if you want to, you can take a look at what's in this data set. This data set has information on the burning times of some tobacco leaves. The predictor variables are nitrogen, which is the nitrogen content by percentage weight, and the chlorine content by percentage weight, and the potassium content by percentage weight, and the burn time in seconds. Now, I know that I'm going to want to make a couple of plots here, so I'm going to set up my plot window accordingly, and I will use this function called log trans. Log trans, that is the function that will take its log of the response plus some number. That is, again, you're taking the response plus a number, taking the log of that. It takes as input our output from our linear model. We want to make a plot. Similarly, this is similar to when we did Box-Cox. Alpha in this case is the constant that we're shifting by before we take the log, and so the alpha values we're going to set to be to range to go between a couple of particular values and move in increments of 0.01. Okay, and now you can see that we get a similar plot as to when we did Box-Cox, except the likelihood function is certainly going to be different. It's a different kind of transformation. Now, note that the confidence interval in this case is not symmetric. It's okay. It's but it's our best guessed value. The alpha value that maximizes this log likelihood function seems to be at about negative 0.8, negative 0.83, something like that. Okay, and so I can zoom in on that value if I change the left and right endpoints. Okay, just set alpha to be a sequence running between these two numbers by 0.01. Okay, and voila. There we go. Zoomed in on it. Because we zoomed in on it, the likelihood function, the log of the likelihood function right there in that little region looks pretty darn flat. We're just moving from here to there is what this plot is right over here. So alpha is about negative 0.835. Okay. So now let's take a look at something else called, this is called broken stick regression. It's, or you can think of it as piecewise regression. It may be that there's some sort of natural way to sort of partition a data set across a predictor variable so that it's sort of linear one way and for some predictor variable values, and then the shape sort of changes sort of depending on what the predictor variable value is. Okay, so let me demonstrate. I'm just going to take the code from Faraway here. First of all, I'm going to get a new graph window, and I'm going to create two linear models. Okay, one is so I'm going to do this with savings data, and I'm just going to make models where I'm trying to model the response SR versus POP 15. Again, that's the percentage of the population that's 15 years of age or younger. And this first model that I'm going to call LMOD 1 is just going to be based on those entries, those records or those observations where those population percentages of ages 15 or under were less than 35. Okay, That is, the population percentages were less than 35. So if you have a population, so if pop 15 is less than 35, then that's sort of like saying that, you know, the population isn't that young. Okay, or if it's greater than 35, if pop 15 is greater than 35, then it means that more than 35% of the population are age 15 and under, so that you have a sort of a younger population. Okay. Now what I'm going to do is I'm going to plot SR, that value, our response variable, against pop 15. And from the savings data, and give it some labels there, and I'll drop a line on there and take a look at this plot. This time, however, I'm dropping a line right down the middle here, because that sort of seems like a natural place to partition the data set according to this population under 15 percentage. Right, and you sort of see how they're sort of two clusters there anyway. So it might sort of make some kind of sense to build to build a linear model in one sector and then build another linear model in the other, and that's exactly what we're going to do. So what I'll do is I'll use the segments command, okay, and I'll do this twice. Again, this is right out of your book. Okay, what I'm going to do is basically just I'm going to make a linear model for these over here, and I'll make a linear model for these over here, and I'll drop these two lines. So that sort of makes some sense. It seems like if remember over here, if the population percentage is less than 35%, then it's indicating that the population isn't that young. So as the youth of the population increases, sort of as the youthful percentage increases, it seems that the savings rate sort of diminishes to a point. And then over here, this is sort of saying that if that percentage increases and gets really high, if the youthful percentage gets to be say up around 40-50%, then it looks like the savings rate begins to go back up again. Okay. Now it may be that that this kind of a model is unacceptable to you or whoever it is you're working for, because maybe that you insist that the mean response is going to be a continuous function of this variable down here. So, and if that's the case, then it may be that what we want to do is try to come up with again another piecewise function that where the two pieces meet in the middle. Okay, so to that end, your author recommends making a couple of functions: left-hand side, right-hand side. Okay, the left-hand side is going to be, we're saying that it's going to be a function of x. Okay, and so if what all this stuff says is that if x is less than 35, then it's going to take the value of 35 minus x. Otherwise, it'll be 0. Okay, and then so this function called RHS will take the argument as an x as its argument, and if that argument is less than 35, it's 0. And then otherwise, on the other side, it'll be x minus 35. Okay, so what I'll do now is I'm going to transform that x variable according to those two functions. Okay, and you should see that those two functions sort of, if I transform that x variable, the pop 15 variable, by LHS and RHS, they don't sort of really add together, because where this function is 0, this function is not, and where this function is 0, this one is not. Okay, yeah, okay, and so now I'll let x be a sequence of values from 20 to 48. I'm just going to tell it where to look here by 1, and then our model here will be, I'll take coefficient 1 from LMOD, which is so that's the y-intercept coefficient from this, okay, plus, look, I'm going to take the slope coefficient, that's the second coefficient there, times LHS of x, and then plus the third coefficient, which is the other sort of slope coefficient, against RHS of x. You can see what's going on here if you do summary of L mod. Okay, you can see that in fact our intercept is 8.6618. The slope on the left hand side then will be 0.3471, and the slope on the right hand side will be negative 0.1040. Okay, all right. So now what I want to do is drop some lines. I'll drop the lines onto the original plot that I had there, and yeah, I'll make them dashed this time. Okay, and yeah, so you can see, there we go. So this way you still sort of get this downward trend on the left, and you also get a downward trend on the right. But so this is what you would get when you're sort of linearly regressing on both sides, but under the constraint where they have to meet here in the middle.